Welcome back, guys. In this video, we discuss the surface area of a surface S given by z equals f of xy over a region R. Specifically, we're going to derive the formula for surface area, and then we're also going to do some examples. So let's say this is our surface given by z equals f of xy, and we've got a couple of assumptions. This region R that we will be integrating over is a closed, bounded region. When we say that the region R is closed, all that means is that it includes its boundary. When we say it's bounded, that just means it's not the entire xy plane. This region R could fit in a circle or a disk if I made the disk large enough. So we've got a closed, bounded region, boundary included, and it's finite. And we are integrating, or we're finding the area of a surface S given by this function, and we want the partial of f with respect to x and the partial of f with respect to y to be continuous on R. Provided those assumptions are true, then we can go through this derivation. So basically what we're trying to do is we're trying to find the area of this surface over here that lies above the region R. Now if this was, let's say it was like a blanket or something, I would be able to take it off whatever it's on, stretch it flat, and then I could measure the surface area by just taking a measurement of length and width, and we can find the area. That's what we'd like to do, but we can't do that here, so we have to use another method. We're going to use calculus to find the area of this surface. But that's the quantity that we're trying to find, is just how big this is in square units, this many units by this many units. Well, the way we can do that is we can take this region R and we can make n subdivisions in the x direction. And we can create m subdivisions in the y direction. And that basically gives us a grid over the region R. So these are my subdivisions in the x direction. And then we'll have m subdivisions in the y direction. And then above each of these little rectangles in the xy plane, we're going to create a parallelogram on the surface. It's basically like taking all of these lines and intersecting them with our surface. So it might look something like this. I'm not doing a very good job. Now each of these little pieces of the surface, and I'm not going to do the whole thing, as they're drawn right now, they aren't parallelograms, but I can approximate them with a parallelogram. If I make this small enough, excuse me, if I make my grid small enough, this is almost linear and this is almost linear. So finding the surface area of this surface can be boiled down to this. If I can find the surface area of one little piece, or at least an approximation of the surface area of one little piece, well then I can add all of those up as I goes from 1 to n and j goes from 1 to m, and then we'll take the limit as the number of subdivisions in the x and y directions go to infinity. And then we'll get a double integral, and that double integral will represent the surface area of this surface over the region R. So it really boils down to finding the area of one piece here, and we can't find the area exactly, but we can approximate that area with a parallelogram. So let's say we're above this region R. Let's zoom in a little bit. We're above this little square, and I'm drawing it on an angle so it doesn't look like a square. I guess it's just a rectangle. But this is delta x units, and that's delta y units. Now to create our little parallelogram up here, approximating that area of the surface, we're going to evaluate the function at this back corner, that corner that's closest to the origin. So we'll come up here, and we'll evaluate that at this corner, which we'll call x sub I, y sub j. So this will be f of x sub I, y sub j. Now to create a parallelogram that looks sort of like this on the surface, I'm going to create a vector here and a vector here that has the same slope as the surface. So if I'm at this point and I'm on the surface, I can find a vector that has the same slope as the surface and points in the x direction here, and I can find a vector that has the same slope as the surface and points in the y direction over here. And those are going to be two adjacent sides of my parallelogram, and then we can find the area of the parallelogram. That'll be the area of one piece, and so on. So let's just focus on finding the area of that one parallelogram. Okay, so if I want to have the same slope as my surface, and I'm going in the x direction, let's say I'm on a vector that looks like this. I'm going to call that vector u. Now u goes in the x direction only. It's u is a vector that's lying above this little line segment that goes in the x direction only. There's no change in y here. So its x component is delta x times I hat. It doesn't go in the y direction at all, so its y component is 0 times j hat, and its z component, well, that is defined to be the slope of the surface in the x direction at that point. So I want to know, well, what is that z component? It looks like the slope in the surface from the way I've drawn this vector. Looks like it must be negative there. Maybe I'll draw my rectangle a little bit bigger. Well, in order to find the z component, I take the slope of the surface in the x direction, and I multiply by delta x. So you could think of it this way. That's the change in z with respect to x. Like maybe it's 4. So that means z goes up by 4 units for every 1 unit change in x. And then we're going to say, well, x isn't changing by 1. X is changing by delta x units. So we'll multiply and we'll get the corresponding change in z. So that's the z component of this vector. Or I can write that this way. And if you prefer, you could call that the partial of f with respect to x. I prefer this notation though because it makes it very explicit that the z is changing. This is a change in z with respect to x holding y constant, and then we multiply by a change in x to get a change in z. Okay, so that's one vector. We're going to do the same thing over here. I want a vector here that has the same slope of the surface as the surface, but goes entirely in the y direction, and it's lying above this line segment in the xy plane. So maybe my surface looks like this. Maybe it goes up in the y direction at that point. I'll call that the vector v. That's a little bit hard to see, but that lies entirely above this line segment in the xy plane. It doesn't go in the x direction at all. It goes in the y direction, delta y units. So it has a 0 component in the x direction, and then we go delta y units in the y direction. At the same time, z is going up by a little bit. Well, that's going to be the slope in the y direction times the change in y. Or if you prefer, you could write that as the partial of f with respect to y times delta y. Now if I put these two pieces together, well, to draw the rest of my parallelogram, I'm going to draw this vector u over here, do the best I can to make it look parallel. And then we'll draw the vector v over here, again, to make it look parallel. The area of that parallelogram is going to be the approximate area of that little piece that's lying above that rectangle there in the xy plane. Now, they tend to use capital S for surface area. Capital S for surface. So the area of this piece, well, that can be found using one of our identities, one of the things that we talked about way back at the very beginning of this course. Remember at the beginning of the course we said the magnitude of the cross product of u and v gives you the area of the parallelogram with u and v as adjacent sides. Well, that's going to come in handy here because that's giving us the area of that little piece. And once I have the area of that little piece, I can add up all of those to get the total area of the surface. Well, first I need to find the cross product, and then I'll take its magnitude. So my components of u are, delta x, 0, and the partial of z with respect to x times delta x. The components of v are 0, delta y, and the partial of z with respect to y times delta y. And we want the magnitude of this cross product, so I'm just going to write magnitude down here. And this might be way too much space, but we'll see. So I cross out the row and column containing I hat, and I get 0 minus this. 0 times this is 0. And then I'm subtracting partial of z with respect to x times delta y. And then we always subtract, cross out the row and column containing j hat. This times this minus this. Well, this times this is the partial of z with respect to y times the delta x times delta y. And then we're subtracting 0. And then we cross out the row and column containing k hat, and we get delta x times delta y minus 0. So we've got this vector here. And notice that we've got a scalar multiple of a vector. We can factor out that delta x times delta y. We see this. And the magnitude of a scalar times a vector is the absolute value of that scalar. We'll assume that delta x and delta y are always positive. And then we take this vector, we take the components, we square them, add them, and take the square root. That's how we find the magnitude of a vector. And typically it's written in the reverse order. And if you take a negative number and square it, it's positive. All right. Now I didn't write x sub I, y sub j on all of this. I guess I should have done that over here as well. But this is the surface area of the ith jth parallelogram that lies above a little rectangle like this in the xy plane. So that's one of them. Now, if I want the total surface area, I need to add those up. So the total area of the surface comes from taking the limit as the number of subdivisions in the x direction and the number of subdivisions in the y direction goes to infinity. And that's just because of the assumption that I made that those subdivisions in the x direction were all going to have equal width. And then subdivisions in the y direction also have equal width. Alternatively, if you didn't want them to have equal width, you could just let the smallest one go to 0. That would be the same thing. So we're going to take the double sum of all of those surface area pieces. And that is the double integral over r of the square root of 1 plus the partial of z with respect to x squared plus the partial of z with respect to y squared. Delta x times delta y, I'm just going to call it dA. This is my preferred version of the formula. You could also use this version. It means the same thing. If z is given by f of x, y, you could do this. But I like to write it this way because it makes it very clear that I'm taking the function z, which depends on x and y, and I'm taking its partials with respect to x and y, and I substitute those in. Now, one common mistake that students make in this section is when you're asked for surface area, sometimes they just integrate over the surface. They find the volume under the surface rather than the surface area. So be careful when you read that problem statement. If it says surface area, you have to do this. And then we'll evaluate this the way we would evaluate any other double integral. So let's do some examples. Let's say I want to find the area of the surface where the surface is given by z equals 9 minus y squared. And we just want the part of this that lies over the region bounded by 3 functions: y equals x, y equals negative x, and y equals 3. Now, in order to use this formula, you absolutely do not have to sketch the surface. But for me, I like to sketch the surface. It helps me to visualize what I'm doing. So I would start by sketching the surface. You will have to sketch the region R so that you can find appropriate bounds for R. Okay, so let's say we're over here, and I've got z equals 9 minus y squared. Well, that's a cylinder. That's just a parabola facing down in the yz plane. When y is 0, z is 9. When z is 0, y equals plus or minus 3. And so our graph looks like this. But remember, if there's no x here, x is free to be anything. So we get exactly the same graph when x equals 1, and when x equals 2, and when x equals 3, and so on. So I would see that same parabola over here. It's kind of hard to draw. Do the best I can. Okay, so that's our surface. Now we don't want the area of the whole surface. We want the area of this surface over the region bounded by y equals x, y equals negative x, and y equals 3. So let's just sketch that over here. Y equals x looks like this. y equals negative x, it's pretty much the same. Just has that opposite slope. And y equals 3 is up here. Haven't done the best job. It should be much more symmetric than that. We'll say not to scale. That's fine. Okay. So what does this look like? Y equals 3 is here, and it looks like we've got part of our triangle where x is positive and part of our triangle where x is negative. So I need to draw my cylinder a little bit farther back. If this is meeting if these two lines are meeting y equals 3, then the corresponding x values are x equals 3 and x equals negative 3. So x equals 3 is right here. And x equals negative 3 is right there. We just do the best we can. Again, it doesn't have to be perfect. We try. Okay. It's rough, but it'll have to do. Okay. And x equals negative 3 is here. So what we see, this triangle actually looks like this. This is the line y equals x, and this is the line y equals negative x. And this is the line y equals 3. So the region R is here. And we want the part of this cylinder that's lying above that triangle. That's what this question is asking us to find. Well, in order to find that area, or in order to find that surface area, we need to evaluate this. So I need the partial of z with respect to x, the partial of z with respect to y. I need to substitute there, and then after I substitute, I need bounds for the region R. Actually, I think I'll do my bounds first because I've already drawn R. Now we could let y go from a function to a function, but then we'd have to change. The bottom function would switch at x equals 0. So the bottom function would be negative x from negative 3 to 0, and then the bottom function would be positive x from 0 to 3. So we don't want to do that. It's easier if we think of our rectangles, think of our region sort of this way. Think of x as going from this function to this function, and y going from a constant to a constant. So I'll do the y part first because it's the easiest. Y goes from the constant 0 to the constant 3. And x goes from this function to this function. Well, if I solve this equation for x, I get x equals negative y. That's my x on the left. If I solve this equation for x, I get x equals y. My x on the right. So we go from negative y to y, and y goes from 0 to 3. So I've got bounds, and the next thing I need to find the surface area is the partial of z with respect to x and the partial of z with respect to y. Or you could use the partial of f with respect to x and the partial of f with respect to y. Either one is fine. Partial of z with respect to x is easy. There are no x's in this, so we just get 0. Partial of z with respect to y, well, there's the derivative of a constant is 0, and the derivative of negative y squared is negative 2y. So then we substitute everything into our formula. So S, that's what the variable that we're using for surface area, is the double integral over R of this, partial of z with respect to x, or it's the square root of 1 plus the partial of z with respect to x squared, plus the partial of z with respect to y squared, dA. And the partial of z with respect to x is 0, and the partial of z with respect to y happens to be negative 2y. And we're integrating from negative y to y for x. So integrate with respect to x first, because x goes from a function of y to a function of y. And then y goes from a constant to a constant. Y goes from 0 to 3. Okay, so that's our surface area integral, and now we just evaluate it. Some of these can be pretty challenging, but we do the best we can. And sometimes it looks bad, but it turns out to not be that bad after all. All right, so we're here. Now remember, when we evaluate a double integral, you start in the innermost integral first. So we are anti-differentiating with respect to x. Well, if this is constant with respect to x, the antiderivative of a constant with respect to x is that constant times x. And then we'll evaluate this from x equals negative y to x equals positive y. So after we've anti-differentiated, we'll use the fundamental theorem, substitute in the upper bound, substitute in the lower bound, and subtract. So I'm just factoring out that this is a constant. The upper bound is y, the lower bound is negative y. We're subtracting those. So this gives me a 2y. Okay, and now we're looking at this. We say, okay, how do we do that? Well, we just anti-differentiate with respect to y. And remember what you always do. You ask first, do I have a basic rule for that? And I don't. It's a product, so I don't. Then you ask yourself next, will U substitution work? And it turns out that it does. This expression under the square root is a good choice for you because it's nested inside another function. We're always looking for composite functions whenever we do a U sub. This has got a function inside a function. Oh, let me get my oven. Sorry, guys. All right. So I've got a function nested inside another function. So if it is a U sub, that's probably my U. And to figure out if it truly is a U sub, I just take the derivative of that. The differential of U is the derivative of this. So that's 0 plus 8y times dy. And I'm not so worried about the 8, I'm worried about the y dy. Since I have a y dy, I know the U sub will work. So we chose U. We computed du, and now we need new bounds. So we need a new upper bound and a new lower bound. And to find the new upper and lower bounds, you just take the original upper and lower bounds and you substitute. When y equals 3, u equals this. And that's 4 times 9 is 36, plus 1 is 37. That's our new upper bound. When y equals 0, well, we get this. I have 0 plus 1, which is 1. So my integral becomes the integral from 1 to 37 of the appropriately substituted integrand over here. Now let's look for all the parts. This part right here is the square root of u by design. And 2y dy, well, I never solved for that, did I? If I want 2y dy over here, I have to divide both sides by 4, or multiply by 1/4, same thing. So 2y dy happens to be 1/4 du, so I'll replace the 2y dy with a 1/4 and a du. And I do have a rule for that after I rewrite it. So we found our new upper and lower bounds. You want to write the integral entirely in terms of u. And then you want to rewrite it as a u to the 1/2 power, so we can use our power rule. Bring that constant down, add 1 to the exponent, and divide by the new exponent. Dividing by 3/2 is the same as multiplying by 2/3. Substitute in 1 and 37 and subtract. 2 goes into 4 twice, so we end up with a 1/6. And then we have 37. I think I said, well, I don't know if I said the right thing or not. That's 3/2. 37 to the 3/2 minus 1 to the 3/2, 1 to any power is just 1. Now this can be simplified a little bit further, just using this fact. X to the 3/2 is the same as x to the first times x to the 1/2, because 1 plus 1/2 is 3/2. So whenever I see this, especially if it's a number, I often think of it that way. So this is really 1/6 times 37 times the square root of 37 minus 1. If you're saying to yourself, what is that? Remember, it's the area of this surface that lies above this triangle. If you're saying, how exactly is that? Like, what is the area? It's this piece. Let me see. It's this surface area right here. That's what we found. That surface area is 1/6 of 37 times the square root of 37 minus 1. Okay, so that's our first one. Now we're going to do more. Remember this formula. If somebody asks you for surface area, this is what you need. Don't just find the volume under the surface. Here's another one. This time we're asked to find the surface area of the portion of the surface given by this, lying above the xy plane and in the first octant only. Now this time they did not give us the region R, so it's implied by this fact that we want the part that's above the xy plane and in the first octant. Remember, first octant, that's where x, y, and z are all positive. We often draw our coordinate system as if we're sitting over here in the first octant, maybe at x equals 10, y equals 10, z equals 10, and we're looking up at it at an angle. That's what we want. We want the piece of this that lies over here. Well, in order to figure out what that looks like, it's helpful to sketch the surface first. So let's start by sketching the surface. And then we'll have to find the projection of the surface onto the xy plane for that part of the surface that lies in the first octant. Well, notice z is raised to the first. X and y are both squared, and they have the same sign. That means you're looking at an elliptic paraboloid. Since both of these are negative, that elliptic paraboloid has been flipped upside down, and then we added 16 to it. So we took our elliptic paraboloid, we flipped it, and we raised it up 16 units. It's the Calc 3 version of transformation. That's all it is. It's exactly like transformations from pre-calculus. And so it looks like this. Now, we don't want the surface area of this entire surface. We just want the surface area of the part that lies in the first octant. Now, the first octant is this part over here. So the region R that we're integrating over is that region. And the first octant part of the surface, I guess probably should have made this a little bit wider back here, is just this part here. Where x and y are both positive and z is negative. So it's, I don't know how to draw it, just to make it clear that it's a surface. It's that part. That's what we want. So we sketch the surface, and then we sketch the projection of the surface onto the xy plane. You want to think of it kind of like a shadow. If the sun were directly above this, where would the shadow lie? Well, it would lie right there. So x and y are both positive, and we have a semicircle. Now to figure out the equation of this semicircle, well, remember, that boundary is given by z equals 0, because in the xy plane, that's where z equals 0. So I'll set z equal to 0. So we have 0 equals 16 minus x squared minus y squared. And then we add x squared and y squared to both sides. So we get x squared plus y squared equals 16. That is a circle with center 0, 0, because we're not subtracting anything from x or y. And the radius squared, that's the right-hand side, that's 16. So r is the square root of 16, which is 4. So that's our region R. Are you thinking what I'm thinking? I hope so. When you evaluate that surface area integral, would you rather be in rectangular coordinates or polar coordinates? I hope you said polar coordinates, because this is really easy to describe in polar coordinates. So yeah, that's where I'm going. We have sketched the projection R onto the xy plane, and the next thing we need to do is set up the surface area integral. And that requires finding the partials of z with respect to x and y. So remember, our surface area is the double integral over r of the partial, or excuse me, of the square root of 1 plus the partial of z with respect to x squared plus the partial of z with respect to y squared dA. And z was 16 minus x squared minus y squared. The partial of z with respect to x is pretty easy to find. Derivative of a constant is 0. Derivative of negative x squared with respect to x is negative 2x. This is constant with respect to x when we're taking a partial derivative, so it's 0. So we just get partial of z with respect to x is negative 2x. The partial of z with respect to y, well, I get 0 here, and negative 2y over there. So here's our surface area integral if we substitute. Replace the partial of z with respect to x with negative 2x. Replace the partial of z with respect to y with negative 2y. And watch this. We get a 4x squared here and a 4y squared here, because you square both factors separately. And that's really nice, because if I factor out that 4, I see an x squared plus y squared, and that is a very nice thing for changing to polar coordinates. So our region R is probably going to be easiest to describe in polar coordinates. And I've got an integram that has an x squared plus y squared in it. So that's going to be easy to describe in polar coordinates as well. So what did we do? We computed our partials. We substituted into the surface area formula. And now, because of the region R, we will change this, or we will write this double integral in polar coordinates and evaluate it. Think about how you would have to evaluate that without polar coordinates. Well, if I'm taking the derivative, if this was 4x squared plus 4y squared like this, and I'm integrating with respect to x or y, that's a trig sub. So you don't want to have to do trig sub. So we can get away, or we can get around that by switching to polar coordinates. So since we're switching to polar coordinates, we need 3 things. So we're writing the double integral in polar coordinates. We need 3 things. We need bounds for R. Okay. Now remember, little r, that's the radius. That's a circle centered at the origin with radius little r. So if r starts at 0, that single point is given by little r equals 0. And if we go from there to there, r is going from 0, it's a circle of radius 0, out to 4, circle of radius 4. Now we don't get the entire circle, and that's okay, but we do get these circles that are centered at the origin, going from 0 out to 4. We just get part of the circle. And to figure out which part of the circle, or to specify which part of the circle, we state our bounds for theta. So theta starts over here and ends over there. So theta goes from 0 to pi over 2. So we've got bounds for r. We need a new dA. dA will be replaced by r dr d theta, or d theta dr, whichever we prefer. And then the last thing we need is a new integrand. So this is 1 plus 4, and x squared plus y squared is r squared in polar coordinates. So let's put all of those pieces together. And evaluate the integral. So this double integral over r, I can write it as the integral from 0 to 4, or the integral from 0 to pi over 2 of the integral from 0 to 4 of my integrand, which is the square root of 1 plus 4, and x squared plus y squared is r squared. And dA is replaced by r dr d theta. Okay, now we've got our integral in polar coordinates. So we will evaluate it and we'll be done. Remember how this works? You start with the innermost integral first and work your way out. So we will start by anti-differentiating with respect to r. Well, in order to do that, let's choose u to be equal to something. let u be an inside function. U is going to be 1 plus 4r squared. Now we know to do u substitution because basic rules don't work, and because the derivative of this, or a multiple of the derivative of this, is up here somewhere. Let me show you what I mean. So we'll do a u sub because if this is my u, du is 4r dr. I'm not worried about, I said 4r, it's 8r dr, excuse me. I'm not worried about the 8, I just need the r dr, and I have the r and the dr. So I'm going to solve this equation for r dr by dividing both sides by 8. And now I can write everything up here in terms of my new variable u rather than r. So this time we happen to use u substitution. So we'll choose u, we compute du, and we need new bounds in terms of u. So we'll replace r with 4, we'll replace r with 0 in our equation for u to get the new bounds for u. When r is 4, we get this. 16 times 4 is 64. 64 plus 1 is 65. That's our new upper bound. And when r is 0, u is 1 plus 4 times 0 squared. So this is 0 plus 1, so we get 1. So over here we've got the integral from 0 to pi over 2. That's the same. Inside, I've got new bounds. My new lower bound is 1. My new upper bound is 65. And this is, by design, square root of u. And r dr is 1/8 of du. So that is our innermost integral. And don't forget that d theta, even though we're not doing anything with it, we should bring it down in order for these to be equal. Okay, so we wrote our integral entirely in terms of u. So we'll rewrite it so that we can use our power rule to anti-differentiate. And we're still focused right here. Add 1 to the exponent, divide by the new exponent. Dividing by 3/2 is the same as multiplying by 2/3. Substitute in 1, substitute in 65, and subtract. And of course 2 goes into 8 4 times. So we end up with a 1/12. And then I've got 65 to the 3/2 minus 1 to the 3/2, which is just 1. I'm factoring all of that out because it's all constant with respect to theta. So I just end up with the integral of 1 with respect to theta. So that's just theta. And any number to the 3/2 is that number times the square root of that number, as we discussed earlier. The antiderivative of 1 with respect to theta is theta, and we evaluate from theta equals 0 to theta equals pi over 2. At pi over 2, we get that. At 0, we get that. So we end up with pi over 24 times 65 root 65 minus 1. And if you're saying to yourself, what was that again? It was this. It was this area, the surface area of the elliptic paraboloid that's lying above this region R in the first octant. Okay, so let me go through the process again with you. We were given this problem statement. They did not give us R. So the first thing we did was we sketched the surface, and then we thought about the projection of that surface onto the XY plane. The projection onto the XY plane, that's the region that we're integrating over. And then we said, okay, we're asked for surface area, so we're going to set up the surface integral. I write down my formula, and I look at my formula and I see I need the partial of z with respect to x and the partial of z with respect to y. I compute those, I substitute, and then I simplify, and I see right away that my integrand has an x squared plus y squared in it. So that tells me maybe I want to switch to polar coordinates. But even more than that, this region R, being a circular sector, tells me I want to switch to polar coordinates. So we decide to switch to polar coordinates. So we get new bounds for the region R. R goes from 0 to 4, theta goes from 0 to pi over 2. We get a new integrand. This is the square root of 1 plus 4 r squared, and dA is replaced by r, which I put out front, dr d theta. Then we anti-differentiate with respect to r. We wrote the integral in terms of u. We had to do some more simplification, and finally we anti-differentiated, and we used the fundamental theorem. And then we anti-differentiate with respect to theta, and then we use the fundamental theorem again, and we simplify. Okay, and all of that got us here, and remember that that's giving us surface area. Okay, I think I will set up one more integral for you, but we'll do that in the next video. But that's pretty much the gist of surface area.